All right, today we're talking about Charles' Law. And Charles' Law was the law that was developed by a physicist who lived from the mid 1700s to the early 1800s. And his name was, let me get the pencil here, Jacques Charles. And so one interesting thing about Jacques Charles is that he was a hot air balloonist. And one of the things he noticed is that when he had his hot air balloon, let's make it look like that, there's the balloon, when he added heat to this, the balloon would expand in size. So the volume would increase. And so what he was concerned with was the relationship between temperature versus volume. And being a scientist, he went out and set out to find a mathematical relationship between these two factors for gases. And so if you take a look at the graph that I have here for you, you can see I have three different gases, A, B, and C. They could be any gases, carbon dioxide, nitrogen, just any gas that exists. And what Jacques Charles observed was that as he heated the gas up, and you can look at gas A, as he heated it up, the gas would increase in volume. Okay? Same for gas B and same for gas C. Even more interesting, if you go backwards and you cool the gas down, you could see the solid line of gas A eventually becomes a dotted line because that's where the gas condenses into a liquid. And as we extrapolate this line back to where it hits the x-axis at zero volume, and think about that, zero volume, that is pretty much the lowest you could go for volume. It doesn't even really exist. The gases would all intersect the x-axis at the same temperature. And that temperature is here. Okay, oops, let me see if I can do a better job of that. That temperature is here. Okay, so no matter what gas you examined, every time you cooled it down and then extrapolated it back to zero volume, you would always end up at the same temperature. And notice that that's well below zero. So that means that 0 Celsius did not correspond to 0 volume. So what scientists did then is they said, we need to invent a different temperature scale which will relate this temperature to volume in a way that is more accurate. And so they took this temperature that is here, which came out to be negative 273 degrees Celsius, and they said, we're going to make that the starting point of a new temperature scale called the Kelvin Scale. And you can see the Kelvin Scale on the x-axis here. So negative 273 becomes 0 Kelvin, and this is the lowest temperature that any type of matter can reach, because if you were to go below negative 273, if you were to stretch down below it, you would be in the land of negative volume. You would be down here somewhere in the land of negative volume. We can't have negative volume. Maybe in the middle of a black hole we can have negative volume, but here on Earth, negative volume can't exist. So therefore, the coldest temperature that can exist is negative 273 degrees Celsius. And we call that absolute zero, which is equal to 0 on the Kelvin scale. This is the temperature at which all motion of particles stops. There is no more movement of particles at all. And this is the lowest temperature that can exist. So now, when we plot the gases A, B, C, D, E, F, any gas in the world, against the Kelvin scale, we see that all of the gases show a perfect relationship of direct proportionality. And what that means is if you double the temperature, you double the volume. If you quadruple the temperature, you quadruple the volume. If you look at this graph of the line here, it's linear and it is constant. So it's direct proportionality from absolute zero all the way up to as hot as you can make this thing. Okay? All right, so mathematically, what does Charles' law look like for us then? So let's go back. Charles' law looks like this. V1 over T1 is equal to V2 over T2, where V1 is the starting volume, V2 is the ending volume, T1 is the starting temperature, and very importantly, that temperature must be in Kelvin, okay, for this proportionality relationship to exist. And then T2 is the ending temperature. And it must be also in Kelvin. So very important that you remember that, because that would be a good way to make a mistake on these problems if you didn't remember to put the temperature in Kelvin. Volume, typically volume is going to be in terms of liters. Okay, oops, I don't want that to happen. Here we go. So volume would be typically in terms of liters, but it could be in milliliters. As long as both of the volume measurements were the same unit, you would be fine. Okay, so we have an introduction right now to Charles' law, and we saw that Charles' law shows us that there is direct proportionality between temperature and volume. And that means if you increase the temperature, you increase the volume. But even more, if you double the temperature, you double the volume. If you triple the temperature, you triple the volume. And what else did we do? We saw how looking at Charles' law with any gas that exists on Earth, when plotted in Kelvin, we can see that at zero volume, the lowest volume you could achieve based on logic, the lowest temperature would be absolute zero. Okay. All right. The last thing is this. You must remember that temperature for these problems must be in Kelvin. Okay? So temperature must be in Kelvin measurement. And I'm going to give you one last formula that you're going to need to use to change from Kelvin to Celsius or back and forth. So Kelvin is going to be equal to Celsius plus 273. So if you're ever given a value temperature value in Celsius, you need to convert it to Kelvin, and you'll do that using the formula that I just gave you right here. Okay guys, so we will be working problems using Charles' law in the near future. These notes are here for you to refer back to once we start working those problems, and they should be posted very soon. All right, thanks.